Hi, my name is Shan Nawaz. In this lecture, we will study the closure of a set in detail, and then we will introduce the notion of interior of a set. But before that, let us recall what we did in the last lecture. So, in last lecture, uh, we studied the closure of a set, and by definition we mean, so if we have topological space, say xt, and so this is our space, and say a is a subset of x, and then we define the closure of a denoted by a bar to be in the union of a with its derived set, i.e. the set of all limit pointers. So this is the set of all limit pointers a prime. So, and we proved in last lecture that the closure of a set is actually a closed set. Now, for example, let us consider the R with the usual topology. So this TU is actually the usual topology. On R. So if we take a subset of Q, say let us take the set of rational numbers in Q. So then for Q, which is a subset of R, we have Q closure is the whole set R. That means this Q closure, which is actually Q union Q prime, is equal to R. Now this means either of the following two sets, I mean this Q prime is either the set of irrational numbers, or Q prime is the whole I mean the set of all real numbers. Now if Q prime is the set of all real numbers, then this union is R. So that means any real number in R is actually a limit point of Q. Let us see how. So suppose this is the set of real the rational numbers, and let us pick any real number here. So suppose x is any real number. So this is in R. So we claim this x is actually a limit point of this Q. So let us pick, suppose there is a real number. So this real number may be a rational or not a rational number. I mean this may be rational as well as or irrational number. So we claim that this point over here, this is actually a limit point of Q, but that means for any open set which contain this Q, this point x here must contain at least one point of Q different from x. Now in R, with respect to the standard topology, I mean the usual topology, the open sets in R are either the open intervals or the union of open intervals. But the basic open sets, I mean the basis of R with respect to this topology, is the set of all open intervals. So recall that we call x in X a limit point of A if for any open set which contain U. So if U is any open set which contain U, then U minus this point must have a non-empty intersection with A. So this should be a non-empty. So in place of U, we are picking an open interval here. Say this is x minus epsilon and x plus epsilon. So now this is the not dotted. It contains both real as well as rational as well as irrational numbers. So in place of U, we have this open interval here, x minus epsilon and x plus epsilon, and in place of A we have Q. Now if I take this interval and let us remove the point x from this interval and look at its intersection with Q. Now this interval contains infinitely many rational numbers. So if we remove x, the intersection is still non-empty. That means this x is a limit point of Q. Now this x was chosen arbitrarily. That means any real number is actually a limit point of Q. So let us prove this. So let us solve this. So we have to prove Q closure is R. So suppose this is not true. Suppose Q closure is not R. This means now Q closure being a subset of R but not equal to R means there is some real number in R which is not in Q closure. Then there exists X in R such that X is not in Q closure. Now X not being an element of Q closure means that X is an element of Q closure complement. So then X is in the Q closure complement. Note that closure of any set is a closed set. So if we take it is complement, the complement of a closed set is open set. That means this Q complement closure is open set. So but Q closure complement being open set, so this would imply, so this implies that there exists, I mean for this point X here, note that a set is open. So let us recall what do we mean by an open set. So if this xt is our topological space and we call a set A in X an open set, if for each X in A there exists an open set U here such that X is in U and U is contained in A. So if this is true for any X in A, then A is said to be open, or in other words this means A is the union of open sets. So now Q complement being open, therefore for this X in Q complement there exists an open set. Now open set in Q usual topology of R means it is actually an open interval or the union of open intervals, but open interval being basic, so there exists an open interval, say x minus epsilon and x plus epsilon, where epsilon is, so where this epsilon is positive real number. So this is, there is an open interval of R, epsilon is positive such that X is in x minus epsilon, x plus epsilon, and this open interval is contained in Q closure complement. But this Q closure complement means, by Q closure we mean Q union q prime, and we take the complement. Now let us use the De Morgan law. This is q complement intersection q prime complement. Now q complement is the set of irrational numbers. So we have an interval over here which is contained in this set, which contain the set of irrational numbers, but this is not possible because this open interval over here, this has rational numbers as well. So this is not possible since x minus epsilon and x plus epsilon contain rational numbers and hence cannot be a subset of this set, which is a set of not the whole irrational numbers but some rational numbers. So hence our supposition is wrong. So hence q closure is actually the set of real numbers. So this is an assignment for the readers to prove. If we take the set of irrational numbers and take it as closure, then this is also real numbers. Now we have the following definition regarding the closure of a set. So let xt be a topological space and A be a subset of X. Then we call A to be dense in X, or sometimes we call A to be everywhere dense, or everywhere dense if the closure of A is whole X. Let us do some examples. So as we have seen above, if we take the topological space R with usual topology, then the set of rational numbers as well as the set of irrational numbers are both dense in R. So first example is consider R with standard topology, then Q and Q complement both are subsets of R such that Q closure is R and Q complement closure is also R. So both are dense in R. Let us do one more example. So let us consider the discrete topological space. So let XD be discrete topological space. Now one should note here that each subset of X is open. I mean, if we look at the singletons of X, they are open subsets, and for that very reason every subset of X has the empty derived set. So then for any subset, say A of X, A prime is empty. This we have seen in the last lecture that the derived set of any set in a discrete space is actually empty. So hence, if we look at the closure of A, which is the union of A and A prime, so A prime is actually empty here, so this is actually A. So this means A closure is A. So the only dense subset of X is X itself. So hence the only dense subset of X is X itself. Let us see one more example. So consider xi, I mean the indiscrete space where this I is indiscrete topology on X. Then in last lecture we have seen if A is any subset of X, then A prime, this is actually empty. If A is empty, it is whole set X minus some point X, say P, if this A is the singleton P, and it is whole set X if A size of A is at least 2. So let A be any subset of X. Then if we look at, then A closure is either empty if A is empty, it is whole X if A is non-empty, because if we look at this case, in that case A prime is this set, and hence A union A prime is this set union A, which is the singleton P, which is whole X. So that means in indiscrete space any non-empty subset is a dense set. Hence A is dense in X if A is non-empty. Now let us characterize the dense subsets in a topological space. So this is the characterization of these dense subsets. So let A be any subset of a topological space, say xt. Then A is dense in X i.e. A closure is X if and only if every non-empty open subset U of X has a non-empty intersection with A, if and only if every non-empty open set, say U of X, has a non-empty intersection with A, that is U intersection A is actually non-empty. So this uh, characterizes the dense subsets in a topological space. So let us prove this. So first we are going to assume that every non-empty open set in U in X has a non-empty intersection with A. So assume that for any non-empty open set U of X, we have U intersection A is non-empty. So we want to prove A closure is X. So this A is any subset of X. So this A can be equal to X. So if that is the case, then so if A is X, then clearly A closure is X closure, which is X. So then clearly A closure is X closure, which is X. So there is nothing to prove in this case. So suppose A is not equal to X. This means there is some point in X which is not in A. Let us suppose that point is X. So then there exists X in X such that X is not in A. Now X not being an element of A means X is in the complement of A. So that is, this X is in the complement of A. Now let us look at our hypothesis. So let U be any non-empty open set of X, I mean in X. So then by our hypothesis, this U has this is non-empty here. Then by our hypothesis, U has a non-empty intersection with A. So then by hypothesis, U intersect with A is a non-empty set. So if this is non-empty and X not being an element of A, we get, so since X is not in A, we have U minus this X intersection A. This is also non-empty because this X is not in A. If X would have been in A, then this intersection, by removing this point, suppose our so this is our intersection, this is empty, non-empty, say this is singleton X. So if we remove X here, then this intersection will be empty, but this intersection cannot be X because this X is not in A. So therefore by removing this X from U, this intersection is still non-empty. Now if you remember the definition of a limit point of a set, we mean a point X in X is a limit point of A if any open set U containing X has this property, that is U set minus X intersection with A is non-empty, then we call this X to be a limit point of A. So this X satisfies this expression here. This is true for any open set because any open set U in X has a non-empty intersection with A. So that means this X is a limit point of A. So this implies that x is a limit point of A, that is x is in A prime. Now this x was chosen arbitrarily in A complement, and this x ended up in A prime. This means this A complement is contained in A prime. In other words, every point in this A complement is a limit point of A. So hence A complement is contained in A prime, because this x was chosen arbitrarily. Since x was chosen arbitrarily from A complement. Now let us look at, so what we have to prove? We have to prove A closure is x. Now let us look at this closure. Now A closure, which is A union A prime, but A prime contains A complement, so this contains A union A complement. Now for any set subset A of x, A union A complement is whole x. So that is A closure contains whole x, but this A closure is also a subset of A, hence this A closure is actually equal to A, hence, and this A closure is actually equal to x. So hence we are done in this case, i.e. this A is a dense subset of x. Now conversely, assume that A is dense subset of x. Now what we have to prove? We have to prove any open set, non-empty open set U in X has a non-empty intersection with A. So we are going to pick, so let U be any non-empty open set in X. So we have to prove this U intersection A is actually non-empty. Let us assume otherwise. Let us suppose this is empty. So we want to show that this U intersection A is actually non-empty. Assume otherwise. Suppose U intersection A is empty. Now if this is empty, that means these two sets, I mean U and A, they share no element. So if X is an element of U, that X is not going to be an element of A. So hence if X is in U, then X is not in A. So if X is not in A, that means, so this implies U set minus X intersection A is empty, as we did here. So this intersection would imply this thing, because X was not an element of A. Similarly, X is not in A would imply this thing. So this means X cannot be a limit point of A, because we are able to find an open set U for which this intersection is empty. So hence X is not a limit point of A. So this is the this is not possible since A closure is X. I mean A union A prime is in X. So this X was not here, so this X has to be here because this X is somewhere in X, and hence this is somewhere in this set. But this X is given to be an element not in A, so this element has to be in A prime. I mean this X is a limit point of A, but we proved here this is not a limit point. So X is not a limit point of A, but this is a contradiction since A closure is X and X is not in A. Now X being an element of X, so this is an element of A closure. So this X lies either in A or A prime or in both, but we are given this X is not in A, so it has to be in A prime. Now X being an element of A prime means X is a limit point of A, but we just proved this X is not a limit point of A, hence our supposition is wrong. I mean this intersection over here is non-empty, so hence U intersection A is non-empty. Now if we look at the closure of some subsets in R under the usual topology, so here's some example. So consider the topological space R TU. By TU we mean the standard topology. So find the closure of following subsets of R. So first one is, so this set contain the element of the form 1, 1 by 2, so on, 1 by n, so on. Second, the set Z of integers. Say we have the set any countable set, any countable subset of not countable any finite subset of R. So let us look at the first example. So if we look at this set, so this is our first example. So let A be our set 1, 1 by 2, so on, 1 by n, so on. So this is the infinite subset. So suppose 1, we have 0 here, so 0 is not an element of this set because 0 is not of the form 1 over n, so 0 is outside of this set. So we have 1 here, we have 1 by 2 here, we have 1 by 3 here, then 1 by 4 here. So as we approach to 0, these points get arbitrarily close. So if we look at 0 near, I mean around the 0, so there will be infinitely many numbers, I mean real numbers of this form 1 over n. So we claim this 0 is actually in the derived set of A, i.e. 0 is a limit point of A. But this is true only when each open set containing 0 has a non-empty intersection with A. Let us look the open sets in basic open sets in R. Those are obviously the open interval. So if we look at 0 here, and let us take a small epsilon neighborhood. So this is 0 minus epsilon, and this is say plus epsilon. Now this set over here, these, now this is the complete set. I mean, there are no gaps here because it's an interval. Now if we look at this portion from 0 to 0 plus epsilon, that is plus epsilon, there are infinitely many real numbers of the form 1 by 1 by n, no matter how small this epsilon is. So for any small arbitrary epsilon positive, we will always be able to find infinitely many I mean real numbers which are of this form. So that means for this open set minus epsilon plus epsilon, if we remove 0 from this set and look at the intersection of this set with A, this is always gonna be non-empty. So this means, this would imply that this 0 is a limit point of A. So now 0 not being an element of A is still a limit point of A. So if we look at the closure of A, that is A union 0. I mean the closure of A is here union with 0. Now this is left as an assignment to prove the closure of Z is Z itself, and closure of any finite subset of R is the finite subset itself. Now let us define the neighborhood of a point. Neighborhood of a point. So let xt be a topological space now a subset n of x is said to be a neighborhood. So as a shorthand, I write the neighborhood by NBD, which means the neighborhood of a point, say this little p in X, if there exists an open set, say U, such that first condition is this X is in U and this U is contained in N, then we call this N to be a neighborhood of X. So let us see what do we mean by this. So we are given a set X and we have a point, say we have a point, say this little p. So a subset N of X is said to be a neighborhood of this little p. So first thing is that this point must be inside the set N. So first thing is that this point, so we call N to be a neighborhood of point P if the condition first is that this X must be an element of N, not X, I mean P. So this P must be an element of N, and there must exist a set, say U of P, which contain this P and is itself a subset of, and then we call this N to be a neighborhood of P. For example, let us consider the usual topology. So consider R with usual topology. So let N is over the interval semi upper interval -1 1. Now this interval contains -1 and 1, so we cannot say n is a neighborhood of this 1 because 1 is not there. So for n to be a neighborhood of some point here, the first condition is that that point must lie inside n. So then n is a neighborhood of 0 because we are able to find an open interval, open set, since there exists an interval, not interval, we call this an open set. There exists an open set because the open sets in R with respect to the usual topology are the open intervals or their union. So there exists an open set, say -12 and half, such that this 0 is contained in -12 and half, and this interval is itself contained in this interval. So this means this n is, this set is a neighborhood of 0 because for this 0 we are able to find this set. But that doesn't mean this n is neighborhood of each of its points, because here if we look at this set n, so -1 is there, but n is not neighborhood of -1. So n is not a neighborhood of -1 because for -1 we cannot find an interval which is contained in this set and contains this -1. Now the open intervals which contain -1 are, so these are the intervals like this. So -epsilon -1 and it is like this, -1 -epsilon -1 plus epsilon, while epsilon is some positive real number. So this is an open set, so this contains -1, but this is not itself contained in -1 to 1 because this -1 to 1 is geometrically like this. So -1 is included and this 1 is excluded, and this interval is like this. So we have -1 here, this is -1 plus epsilon, so it is not included, so we write a circle here, and we have -1 minus epsilon. Note that this open set is not here because these elements are here, but this portion is not there. The points left to the -1 are not there, so this is not a neighborhood of -1. So the reason is since there exists no open set. Now when I talk the open set, one should remember the topology with respect to which we we are taking our open sets. Now we have the usual topology here, so by open set in this topology I mean the open interval or the union of open intervals. So there exists no open set U in R such that -1 is in U and U is contained in this interval. So this is not going to be a neighborhood of this point. Similarly, if we look at the set of rational numbers, so this is example second. So if we look at the set of rational numbers Q, So we have the topology R under the standard topology. So Q is a subset of R. So we claim Q is not neighborhood of any of its point. So if R is in Q, that means R is a rational number, then there is no open interval which contain R and is contained in Q, because this interval over here contain both rational as well as irrational numbers. So an interval cannot be a subset of Q. So then there exists no subset U, this is open, subset U in X such that R is contained in U and is contained in Q. Similarly, Q complement either set of irrational numbers is not neighborhood of any of its points. However, Q R, if we look at R is neighborhood of each of its pointers, because for any real number, say A in R, we are always able to find an open interval, an open set like this, and which is contained in R. So R is neighborhood of each of its points. So one should remember we are taking the usual topology. So there are sets which are not neighborhood of each of its points. I mean, there are sets which are not neighborhood of any of its points, and there are sets in a topological space which are neighborhood of each of its points. So in next lecture we are going to prove that the closure of a set is actually the smallest closure set that contains A, and then we are going to define the interior of a set, and we are going to prove the interior of a set is actually the largest open set contained in A, and we denote the interior by A, this circle here. So this is the set of all pointers of which A is a neighborhood. So this A interior is actually the largest open set contained in A. So this we are going to prove in next lecture.